So the Bruce Kelley 1929 CW contest comes around once a year in November for 2 weekend sessions of 24 hours each. It allows us to use these old-time circuits, which are mostly Hartley oscillators, Colpitts oscillators, tune plate, tune grid, TNTs. These are all the circuits that were used in the 1920s. You have to use a period tube that is a tube type that was developed before 1929. And you have to use the circuit that they had during that time period and not use some more modern type circuitry. You can use almost any materials, however. So the contest recognizes that it's very difficult to get period parts. We do strive to use period parts in these transmitters, but you use what you can use with the tubes that they approved. And the particular tube I'm using in this 1929 20-meter Hartley oscillator is the type 211 triode. The 211 triode is very popular for the audiophiles for Class A single-ended amplifiers. And of course this is a 1920 style tube, but directly heated filament, the whole thing. But this thing's gained popularity again suddenly after being completely ignored until it was discovered by the audio people in the 80s and 90s. So this oscillator on 20 meters, of course, it's very difficult to make an oscillator stable on 20 meters, even if it's 10 milliwatts, much less a 10-watt output power oscillator. This device really goes. So we'll take a close look at this circuit and see if we can make a stable 20-meter transmitter that we can put on the bands without causing mayhem. This is a reprint of the first edition of the Radio Amateur's Handbook by the American Radio Relay League. The ARRL put this out in 1926. Okay, 1926 for this manual. The only thing I wanted to bring your attention to in this handbook is there's a lot of transmitter information in this handbook, and this is one of the beginner projects in there, a simple Hartley oscillator to get you on the air. And I wanted to show you the number of taps that are on this transmitter. There's taps galore, 1, 2, 3, 4, 5 taps alone on the main coil. So I just want to get you used to the idea that playing with tap position on a Hartley can improve your performance. And by experimenting around with taps, you can go a long way to improving the chirp, the drift characteristics, and the quality of the note that you get. So I just want to get out of your mind that a Hartley oscillator has 3 connections. It can have more than 3 connections. One of the more difficult bands to handle, however, is 20 meters. A lot of people avoid 20 meters with these simple transmitters, just like people avoid 630 meters because of fear of the antenna. It's just too much work to try to make something stable or work on 20 meters. Imagine a power oscillator that puts out from 5 to 10 watts on 20 meters, 14 megahertz? How would you ever get that stable? I can't even get my 80-meter one-tube Hartley or TNT stable. How do you expect me to get a 20-meter transmitter stable using a self-oscillating tube circuit like a Hartley or a Colpitts or a TNT? So anyway, this year I decided to build myself a 20-meter Hartley oscillator, and that's what this is. And I went through some trials and tribulations, but I think I've got something that works. And I'm using some different techniques than we're used to. However, they're all techniques that were known in the 1920s. And one of the most important ones is the rigid inductor. Notice this inductor is not made out of copper tubing, it's made out of copper strap. Solid copper strap, supported in 3 places. That's a big key to getting stability, cutting down vibration. The other technique is to use a metal front panel, which certainly was known in the 20s, but most of these breadboards you see today are open with no absolutely no protection from hand capacity effects. Anyway, this is the 1929 CW contest on 20 meters. Let's do some DX.
So how about a quick Hartley oscillator review? Hartley oscillators are inductively coupled voltage feedback variable frequency oscillators. The oscillator may be series or shunt fed, meaning the DC can go in directly to the coil, to the plate, or it can go in through a coupling radio frequency choke. The Hartley oscillator has the advantage of having one center tapped inductor and one tuning capacitor. This arrangement simplifies the construction of the Hartley oscillator compared to other types. This circuit is practical because it requires only a single variable capacitor to tune it, and the parts count is small. The circuit is characterized by a single continuously tapped coil, but this is actually not necessary. The coil could be split into two separated coils and it would still function, usually at lower efficiency, however. With a linear harmonic sinusoidal oscillator, such as the Hartley, in order to oscillate with stability, you need a driving source and a way to feedback the signal on one frequency in phase. So a tuned circuit is used as the phase reversal method that reverses the 180-degree flip of the tube back to 360 degrees with the tuned circuit and the center tap. The center tap effectively provides this flip, and the circuit is self-energized for efficient Class C operation. With the grid bias circuit, the oscillator must produce a very stable frequency, so the tuned circuit must not be affected greatly by the driving circuit. Or the load. The load in this case is our antenna. It does not want to be influenced by temperature, or time, or hand capacitance, or any other effects. This is facilitated by using very low loss, highly selective tuned circuits and isolating them from our body. Like coupling to the load. Because a high Q resonator requires less driving power than a corresponding low Q resonator, its frequency is less affected by a given fractional change in the driver system. Tube circuits won't affect a high Q circuit compared to a low Q circuit. The series circuit shown is the simplest implementation, and it's still quite popular in radio design. But our Hartley has to generate large amounts of power, so the voltage on the main coil can be embarrassingly high, upwards of 200 to 500 volts DC. The modification of the circuit to shunt power feed removes this high voltage from the coil, thus making it less of a hazard to the operator. This shunt circuit was popularized for ham radio use in the 1920s by Ross Hull, an Australian and the first ARRL technical director. When one starts to play with additional taps and tapping down on the basic Hartley, either from the plate side or the grid side, some additional stability characteristics could be attained at the higher frequencies. This is analogous to the clap oscillator version of the coal pits. Grandpa did this experimentation with all of the taps we see in the early Hartleys and that 1926 Radio Amateur Handbook. Later, these Hartley techniques would actually be formalized and described by G.F. Lampkin and Vacker and others, and these would be utilized in the famous BC 221 and other frequency meters. Here are a few Hartleys built by some of the 1929 contest enthusiasts. Most are shunt-fed for safety.
So we're going to be keying it with the regular key. Let's look at the frequency as we key it and see what happens. I'm into a dummy load. The frequency is going down. Now this is natural for most Hartley oscillators. As a matter of fact, it's natural for most oscillators for the frequency to go down, because once you start to put current through capacitors, they tend to increase in value. and that causes the frequency to shift downward. So a simple single tap Hartley oscillator, as built, will always tend to drift low. It's usually not a problem when you're sending code because you're not actually keyed down all the time, so the tube doesn't really heat up the parts as much as you're keying. But in general, your frequency will start to go down. Now, one thing we can do with the Hartley is we can add a fourth attachment to the coil. Right now we have 3 attachments: the top and bottom of the variable capacitor, that's our tuning, and our center tap, which is grounded. So we're going to add another tap, a second tap to the coil. So I've just moved the tap from where it was connected at the base here, and I've gone up about a quarter turn. The tap is now a quarter turn up, going to the grid of the tube. Okay, with the tap point about 1 turn down, the oscillator is completely stable. If we continued to go down the coil, 2 things would happen. Our feedback would start to reduce, but it would start to creep upward in frequency. So by adding a second tap to the Hartley oscillator, we've stabilized a 10 watt, 20 meter power oscillator operating at 14 megahertz, something that's thought to be almost impossible with these transmitters. Of course, when you do this, you have to readjust your frequency because it lightens the loading on the coil and changes the feedback somewhat. But it's not a big adjustment. Now on this transmitter I have 2 controls. I have a coarse tuning control and I have a fine tuning control. Once you get to 20 meters, you need to have some type of fine tuning, and in my case I'm using a 10 picofarad capacitor that brings a little bit of capacitance to one side of the coil and allows me to do somewhat fine tuning. You do not want this thing on a table that's going to vibrate a lot. Okay, let's look at the power meter. Okay, almost 10 watts out. So of course, anything you touch on this is going to change the frequency. So when you hook this up to your antenna, you want to make darn sure you're grounded properly, you have a good SWR to the antenna, and the antenna needs to be as stable as possible. If it's a dipole, make sure that dipole is completely rigid with good, strong rope on each end of the dipole, making sure it's not going up and down, because on 20 meters, I can assure you, it will change the frequency of this oscillator. So this is an example of a power oscillator on 20 meters. It's putting out a signal that we would consider to be slightly dirty and drifty. You probably won't be able to work my station with your modern radio set for a 400 cycle bandpass. You need to open it up to 1 kilohertz in order to keep me in your passband so you can even hear me. So I wouldn't expect that anyone with a modern transceiver would be able to work me with this transmitter, because I might drift off your frequency or be slightly off your frequency so you'd never even hear me. On this particular contest situation, however, people are using receivers and they're tuning around and deliberately looking for the dirtier signal, for the signal that might be drifting around a little bit or have some chirp. So that's the situation with this contest. People are actually looking for these signals instead of rejecting them. Typical RSTs might be 477, 497, 496. Those are the types of signal reports you might get in this contest. And those are completely legitimate RST numbers. Let's take a look at some of the interesting construction techniques on this transmitter. Again, we strive to use period parts, but as you start to build these, you realize that you might not have the part needed. So as you can see, I'm using postage stamp capacitors that probably are a little bit later than 1929. I'm not sure if they were in production in the 20s. They might have been. I'm using modern terminal strips over here. Okay. Certainly the tube socket and the tube are period. The variable capacitors period. The use of copper as a coil in this big ceramic standoff, that's all period. But again, you do what you can with what you have, and you improve it year by year, substituting the newer parts for period type parts from the 1920s, and also the front metal on this. Certainly they used metal chassis in the 20s, but most of the transmitters that you see will strive to be a pure breadboard type construction. Here on 20 meters, though, I wanted to have that extra stability that would be afforded from a grounded front panel. So again, the main tuning is on a vernier drive. That's a set and don't touch it again type control. And then the fine tuning is this small 10 or 15 puff style trimmer capacitor. So that's the main tuning for 20 meter CW portion. The filament transformer is on the breadboard. That's typical for these things, that you put the filament transformer right on the breadboard. The tube is going to get warm, so that's another thing that could influence your tuned circuit, and perhaps the heating effect of the tube against the tuned circuit could upset your stability. So it's a good idea to space that out to make sure that the heat from the tube has someplace to go up here. And this should work okay. So anyway, this is the construction technique for a fairly stable, fairly good note 20 meter power oscillator capable of 8 to 10 watts output with 25 watts of input power. Okay, the main tuning is right across the large variable capacitor. This tap here goes to ground. That's your center tap. Notice the big ceramic standoff is supporting the coil in the middle for extra stability. The output link is a little bit light. This could vibrate possibly, so maybe you want to use heavier wire than that as your output link. Basically, coming in and out with that link is how you adjust your coupling. I do have some capacitance on the ground side of the link, approximately 300 picofarads of capacitance, and I can tune that also to affect loading. And then I'm using a modern SO239 connector on a very rigid output bracket. So there we go. That is the 1920s style Hartley oscillator on the 20 meter band, which is a very difficult band to get a VFO to work on, much less a 10 watt power oscillator. Some of the features of this Hartley oscillator that might be interesting to you. This is a shunt-fed Hartley. That means that there's a choke down here, and the B plus is going through that choke, and we're actually capacitor coupled to the tuned circuit. So even though there's high voltage going to the tube, the tank and both sides of the capacitor are completely cold. Everything over here is cold for high voltage. And that's a very good safety feature. So in order to get to high voltage, you've got to try a little bit. Now, this side of the coil is connected to the frame of the capacitor, which is the grid side. Here's the grid tap. Here's the grid components coming in, the grid leak. The other side of the capacitor, that's this part here, is connected to the plate side. The plate going to the choke and the coupling capacitor. So grid side, plate side, and the middle goes to ground. The middle of the coil is grounded. So you can put the tap either on the plate side, see I've come up on the plate side some, or you can take the grid, disconnect it from here, and bring the grid up the grid side. Those are two ways you can play with the taps. And each way might give you something that you're looking for. Better note, less chirp, less drift. So experiment with the taps both on the grid side and on the plate side. I opted to go with the plate side, so I brought the plate coupling capacitor off the choke about a half a turn up. And that gave me the best place for my particular situation with this 20-meter oscillator. Some other things you might notice on this transmitter, I have a brace on the front panel so the front panel doesn't flex. Even this much flex causes the frequency to go woo, 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 woo. Okay, you don't want that. Also, you'll see that we have an additional bleeder resistor on the B+. My power supply doesn't have great regulation, and since it is a choke input type, by putting a little bit stiffer bleed on it, you can get better regulation. Again, we have the onboard filament transformer, and I've got parasitic chokes here. I have a parasitic choke on the plate circuit. This is the plate terminal. This is the plate choke. This is the coupling capacitor that goes to the tap that I use on the plate side of the inductor. This is the grid side. The grid side is the frame of the capacitor here off this grid leak system here. This is the fine-tuning control, which just simply connects from ground to the grid, and it's just offset balancing. It's just providing a little bit of adjustment of the frequency. I could have come off either side and it probably would have worked fine. Anything other than ground and it probably would tune this thing. Notice the extremely loose coupling on the output. So we're getting, if I went very close coupling, I could get over 10 watts out of this oscillator and the current would go out of sight. By loose coupling, bringing it down to 5, 6, 7 watts instead of 12 watts, the note does improve markedly. So loose coupling on 20 meters means really loose compared to what you're used to on the lower frequency transmitters. So I had to adjust the tap just a little bit more because the drift was just slightly going down as I keyed. Now it's slightly going up at first, but then it stabilizes. Absolutely nuts. 575, that's not bad. Oh, 595, that's even better. Good DX.